Yes.
كنسمعك شكرا بزاف. الله يودي شكرا بزاف على الانفيتاسيون، فرحان بزاف حيت عيطتوا عليا ندير هاد التورك مع ام دي اس. انا بريزونتي وقيلا بالونجلي ياك. اوكي. So can I share my screen? Okay. Do you see my screen? Okay. So the talk will be about algorithms with predictions, also called learning augmented algorithms. So very quickly, the structure of the talk would be as follows. In the beginning, I will just talk in general about how do we measure the quality of an algorithm in theoretical computer science, because that would be useful in the rest of the talk. And then I'm going to discuss how to use side information, which is learning augmented algorithms. That I'm going to define more formally in the third section. And finally, I'm going to talk about some applications from some papers I worked on, and also some other applications that I found very interesting in other papers. So for the first section, in general, in a problem of decision making under uncertainty, I'm going to explain with this simple example. Imagine I have some amount of gold, or let's say Bitcoin, that I want to sell. The problem is that I don't know what is the best time for selling, since the price is constantly changing. So now imagine I have a period of time, let's say a window of 1 month, for example, and I want to sell before the end of the month. The problem is that I don't know how the price will evolve during this month. So what I do is that I will observe how the price evolves, and at each step I should make a decision of either selling the gold I have and get the money, or wait to the day after to see what happens. So the problem is that it is a problem of decision making and the uncertainty. I have no idea how the price is going to evolve from one day to another, and there is no clear strategy that guarantees that I will sell at the maximum price, because the maximum price can really be anywhere in the sequence. So in this situation, the first question is how to make a decision on when to sell. And formally, we can define the solution to this problem as an algorithm. So an algorithm is something that will simply take into account the previous data and how the price has been evolving in the last days or last weeks, and this will give me a decision on when to sell. So this is just, we define an algorithm that tells us when to sell. Okay, now that we have an algorithm, how do we know if the algorithm is good? For example, an algorithm can be sell at the end of the first week. So this is an algorithm, but it is a good algorithm. Not necessarily, but so yeah. So to say if an algorithm is good or not, we need to have guarantees on the algorithm. Now, what types of guarantees can we have on algorithms? In general, we can have worst case guarantees, which are very used in computer science, or we can also have guarantees in expectation. So very quickly, I'm going to talk about worst case guarantees and guarantees in expectation. Now, for worst case guarantees, if we consider some algorithmic problem, any algorithmic problem, you can think of sorting a list, graph search, data structure. So everyone with a background in computer science can relate to some problem, some algorithmic problem. And I mean, for example, if we think of sorting, the quality of the algorithm is measured by the time complexity and the space complexity. In other problems, it also makes sense to look for good approximation constants. If, for example, the problem is NP hard and we can't find an optimal solution for the algorithm, we can just find an approximation of the optimal solution. And in that case, we want to find a good approximation constant. There is also a notion of competitive ratio that is used in online algorithms, and there are a lot of ways to measure the quality of an algorithm, a lot of metrics to measure the quality of an algorithm. But in all these metrics, we will look at the worst case. For example, when we talk about type complexity, we will look at what happens in the worst case. So why are we interested in worst case guarantees? Because if we have a guarantee in the worst case, it eliminates any possible risk. If I give you a worst case guarantee, you are sure that this is always true. Now, how can we obtain worst case guarantees? It is necessarily to do a theoretical analysis of the problem to obtain such guarantees. Uh, in more empirical research, it is possible to just experiment the algorithm we have on a lot of benchmarks, on a lot of different data. And if the results are always good, we can say that the algorithm is good. But this is not enough to prove worst case guarantees. Okay, so for worst case guarantees, we really need to do some theoretical analysis of the problem. And now once we have an algorithm and we have worst case guarantees on the algorithm, how do we know that our algorithm is good or if it can be improved? So to do this, we prove impossibility results. So in general, we prove an algorithm that have some level of guarantee, and we'll prove that no algorithm can have a guarantee exceeding this one. So to explain all of this, we will look at the example of worst case guarantees for the sorting problem. So imagine we have a list of values x1 to xn that we need to sort. So if we look at the worst case guarantees, so the best case if the list is already sorted, and the worst case is the list can be really anything. So there are multiple sorting algorithms. We have bubble sorts, insertion sorts, quick sorts, merge sorts, and many others. If we look at the best case, well, bubble sort, if in the best case, has a complexity of big O of n, which is very good because we can do better than n. We need at least to read all the values in the sequence. So it has a complexity of big O of n, but in the worst case, it has a complexity of big O of n squared. The same goes for insertion sorts. For quick sorts, we have big O of n log n here and big O of n squared here. And for merge sorts, we have big O of n log n in the best case and in the worst case. So for any sequence, we have a complexity of big O of n log n, and the algorithm does not benefit from the fact that the sequence might be sorted in the beginning. So among these algorithms, which one should we use in general? If we have a problem of sorting a list, which of these four algorithms will we use in general? Well, the answer is merge sorts. Merge sorts because it tells me that for any possible sequence, for any possible input sequence, the complexity is always n log n. While for bubble sorts, insertion sorts, and quick sorts, if I have a bad sequence, the time complexity can be as bad as n squared. Okay, so now that we have a sorting algorithm with n log n as a worst case guarantee, now the question is this complexity good? Or should we try to find another algorithm? So at the beginning, when someone came with the bubble sort algorithm, the worst case guarantee was big O of n squared. Here it was possible to just stop trying to find better algorithms. But it was also possible to try to look further. So someone came up with merge sort algorithm with a complexity of big O of n log n. Now here again, the question is, should we stop here or should we look for something better? And to answer this question, we should prove impossibility results. So the impossibility result for the sorting problem tells us that the worst case complexity of any sorting algorithm cannot be better than big O of n log n. So this complexity of n log n is the best possible, and there is no need for trying to improve it further. So another approach to prove guarantees is having guarantees in expectation. And guarantees in expectation make sense when we know that the input follows some distribution, some probability distribution, and we exploit this distribution to improve the performance. So for example, if we assume that the list x1 to xn is a list of values that are sampled from a uniform distribution in 0, 1, So we can have an algorithm. The algorithm is bucket sort. Maybe some of you know it already. So we can use a variation of bucket sort to have a time complexity for sorting that is just big O of n in expectation. So the average time complexity is big O of n. But the worst complexity, the worst case complexity is big O of n squared. So the good thing is in guarantees in expectation is that, so yes, we have something in expectation that is better than n log n, but it only holds for this particular sequence. But if we have a sequence that is not exactly the same, or if we look at a particular realization and not on the expectation of the time complexity, then it can be as bad as big O of n squared. So for these two approaches, worst case analysis and stochastic assumptions or expected guarantees, both have some limitations. The limitation of worst case analysis is that in general, the guarantees are very limited. So we have some impossibility results that we cannot go beyond. And the problem in these impossibility results is that they are overly pessimistic. Because if we look at data, for example, if we think of the example I gave earlier of the price of Bitcoin or the price of gold that will be varying, it's true that it is very random, but it follows some pattern. And such pattern is not taken into account when we do worst case analysis. Now, in stochastic assumptions, if we have stochastic assumptions, we will follow the we will assume, sorry, that the input follows some distribution. But the problem is that, as I explained for sorting, that the guarantees only hold in expectation. So in the average case, if, for example, I have a problem that I will solve multiple times, it's okay to have guarantees in expectation because so I will play the same problem or the same game 100 times, and on average I will have a good performance. But if I'm only playing once, so if I look only at one realization, I don't have any guarantees. And also, it is difficult in practice to know the distribution of the input. We can, for example, the objective of machine learning, of a lot of machine learning algorithms, is to approximate some distribution, but we can never know the true distribution of the inputs. We can just approximate it. And with just an approximation of the distribution, it is not clear how if the guarantees that we prove theoretically stay true in practice. So now we move to the second section, which is on how to use side information, and I will explain what I mean by side information. So imagine I want to find some word in a dictionary. So the word washlabas begins with the letter W. If I want to search this word in the dictionary, naturally I will not open the dictionary in the middle, but instead I will open it in well, somewhere near the end of the dictionary. But this is not what is done in search in the worst case. So yes, so more explicitly, finding a word in a dictionary is exactly the same problem as finding a number in a sorted list. So imagine I have a sorted list here and I am asked to find the number 27. So to do this, the best possible algorithm is binary search. So binary search will first look at the middle index, and so we observe a value of 16. Since the list is sorted, 27 is somewhere to the right. We will again look at the subproblem on this list here to the right. We will again access the middle index. It's 31. So here we know that we should look somewhere between 16 and 31, and we find 27. Okay. So in general, if we want to find a number in a sorted list L of size n, with this algorithm binary search, so it has no assumptions behind, the complexity is always big of log n operations or comparisons. And this is the best possible. Now, if we have some stochastic assumptions of the inputs, for example, if we assume that the values in the list are not arbitrary values, but instead values from some non-distribution f, then we can have a better algorithm that is called interpolation search, which has a complexity of log n in expectation instead of just log n, which is much better. But again, the problem here is that we have this assumption here that is not always true. Now, if we want something in the middle, so in the example I gave with the word washlabas, so the word starts with W. So yes, we want to say that somehow we want to open the dictionary somewhere in the end instead of opening it somewhere in the middle. So this is somehow equivalent to saying that the algorithm is given a prediction y of the true position x of the number v that we are looking for in the list n. So for example, here is the list again. I want to find the number 27, but then someone tells me, or some machine learning model or anything, so I have a prediction that tells me that 27 is in the position y. So y somewhere in the beginning of the list instead of opening in the middle. So what I do is that I will look what happens in this index y. I find the value 10, and then I will do what is called an exponential search. So in exponential search, I will see what happens at the index y plus 2, then index y plus 4, y plus 8, and observe here that the step is increasing as powers of 2. So then I will look at y plus 16, and so here once I know that I have a number that is larger than 27, I know that 27 is somewhere in this sublist, and I will just do a binary search here, and I find 27. So this algorithm has a complexity of big O of log x minus y, which is the distance between the true position of 27 and the predicted position of 27. And why is this a very good guarantee? Because so the prediction error is never worse than n, and so we always have big O of log n if the prediction is bad, and I lose nothing compared to the standard binary search algorithm. And if the prediction is good, so if y is equal to x or at least close to x, I have a complexity that is constant. So even if in a very large list, if the prediction is good enough, I can find the target in a constant type. And so this is a huge improvement over classical binary search. And this approach was introduced in a relatively recent paper by Likuris et al. So yeah, the paper was cited here before. Yeah, so by Likuris and Vasilvitsky in ICML 2018. ICML is one of the major conferences in machine learning. Yes. So a second example is the rent or buy problem. In this problem, imagine that you have a trajectory from your house to the works to your workplace that you need to do every day. And if it is sunny, then you just trajectory afoot. But if it is rainy, then you need to take a bus, and so the bus has a certain cost. The cost for buying a single bus ticket, let's say it's one unit. So yeah, 1 unit can be maybe 4 dirhams or €1 or anything. So the cost for a single bus ticket is 1 unit, and the cost for subscription for 1 year is B. So B units of the cost. And the question is, should we keep renting? So keep buying tickets, or should we just buy the subscription for 1 year? And optimally answering this question depends on the number of raining days. So if we call the number of raining days x, it is unknown. So the number of raining days during the whole year, it is unknown in advance. And if, let's say, if we know x, then we can have an algorithm that will have a cost of buying and renting that is minimum between x and b. So if x is smaller than b, I will just rent for the whole year. And if b is smaller, then I will just buy at the very beginning. And the problem is, of course, x is not known, so I cannot have these costs exactly. Now imagine so since I don't know x, I need to decide when to buy. And so let's say I will denote by alg bx, so alg for algorithm, the total cost of renting and buying paid by an algorithm that I follow. So my algorithm will tell me, for example, rent for 10 days, and if it keeps raining, then you buy a subscription. Okay, and so yes, so alg of bx will be the total cost of renting and buying given the price of buying the subscription B and the number of raining days X. And the objective is to have a cost paid by my algorithm as close as possible to minimum XB, which is the best possible. So we can prove that for any deterministic algorithm, there exists a worst case instance Bx such that alg of Bx is larger than twice minimum Bx. So this means that I cannot have an approximation to the optimal value better than 2. So just as a parallel between what I'm presenting now and what I'm presenting and what I presented earlier, Earlier, I talked about binary search and about sorting algorithm. In these problems, the evaluation metric was the complexity, while here the evaluation metric is this approximation constant. Okay, so how close can I get to the minimum between b and x? And this theorem tells me that I cannot be closer than 2. Now the question is, can we have an algorithm that will pay at most twice minimum b and x? And the question is yes. So the algorithm simply consists in renting for b days, then buying. So if the price is 20, I will just rent for 20 days, and in the day 21 that it rains, I will just buy a subscription. And this algorithm satisfies that for any x and b, the cost paid by the algorithm is at most 2 times b and x. Okay, so this is the worst case analysis. But again, the problem here is that this is a very pessimistic scenario because in general, the number of snowing days, the number of raining days, sorry, can be approximated based on past data. So this is what we can do with AI. So imagine we have an additional input, which is a prediction y of x. So an AI, a machine learning model, tells me that the number of raining days in my city is 70 days. So this is, of course, based on past data, based on what happens during the last years, and also on what's happening right now in neighboring regions. So yes, it's all the technology behind the forecasting for weather. And so I have a prediction that tells me the number of rainy days is 70. The problem is that I don't really have any guarantees on the quality of the prediction. So this prediction can be obtained from a large language model or a forecasting model that has as many parameters as possible, that has been trained on as many data as possible, but still I don't really have a guarantee that this is true. So I want to use the prediction because I have some confidence in it, but still I want to be precautious. So what I will do is that uh, if the prediction, if y is larger than b, so if y is larger than b, the optimal decision would be normally to just buy, if I just follow the prediction. The optimal decision would be to buy at time 0. But what I'm going to do is that I'm going to follow the prediction with some precaution. So the precaution is that instead of buying at time 0, I will buy at time lambda times b, where lambda is some constant in 0, 1 that I choose. And if the prediction y is smaller than b, then if I follow the prediction, I will never buy. So I will just keep renting because, well, if x is equal to y, I won't have to buy because x is smaller than b. But then I'm going to trust again the prediction, but take some precaution. So the precaution is again, so with the same constant lambda, I will buy at day b divided by lambda. So if at day b divided by lambda, it's still raining, I will buy and I will no longer trust my prediction. So this algorithm, so again, this problem with prediction was studied in a paper that was published in NeurIPS 2018, which is also a top conference in machine learning. And so the authors proved that the algorithm I have just described right now has a, yes, so the cost paid by the algorithm is at most 1 plus 1 divided by lambda minimum x and p. So this is true for any b, x, and y. So even if the prediction is arbitrarily bad, I always have these constants. This is independent of the prediction. But in the same time, now if the prediction is correct, so if the prediction is correct, this term x minus y is equal to 0, and I will only buy, and I will only pay 1 plus lambda times the minimum between x and b. So this is called consistency. The red constant here is called robustness. And the third term here tells me how my error, how the performance of my algorithm degrades as the error increases. And this is called the smoothness of the algorithm. So this is, I will take some time on this slide because it is very important to understand what's happening here. Here, if my prediction is perfect, then I am paying just 1 plus lambda. Imagine, for example, that lambda equals 0.5. So here, if the prediction is perfect, I will just pay 1.5 minimum xb. While in the scenario without predictions, I was paying 2 times minimum xb. So here I have a beta constant, which is 1.5, if the prediction is accurate. And if the prediction is not accurate, so if the prediction is anything, I'm never worse than 1 plus, so 1 over 0.5, which is 3. So I will never pay more than 3 times minimum XB. This is worse than the constant 2 that I had earlier, but this only happens when the prediction is arbitrarily bad. And then how the interpolation is done between these constants 1 plus lambda and 1 plus 1 over lambda, it depends on this error term. So if we want to visualize this on a figure, so the case lambda equal 1, if we take lambda equal 1, so this constant here is equal to 2 and this constant is equal to 2. So for any prediction error, my algorithm will always have an approximation constant equal to 2. Okay, so this is oblivious to the prediction. Now, if I choose a constant lambda equals 0.1, so choosing lambda equals 0.1, this means trusting the prediction almost 100%. So if I do this, if the prediction is accurate, then I will have an approximation constant very close to 1. But in the counterpart, if the prediction is arbitrarily bad, my performance also becomes arbitrarily bad. Now I can choose some intermediate values of lambda. For example, lambda equals 0.5. So for lambda equals 0.5, if the prediction is accurate, I have an approximation constant of 1.5 instead of 2, which is better. But then as the prediction becomes worse and worse, my performance also degrades, and I obtain by the end, if the prediction is arbitrarily bad, an approximation constant of 3 instead of 2. And the good thing in this algorithm is that I am the one who chooses this constant lambda, this parameter lambda. So if I want to trust the prediction, I will set lambda closer to 0. And if I don't want to trust the prediction, if the prediction is given by some bad model that is not proved to be good enough, I have more advantage in choosing some lambda that is closer to 1. Okay, so this is what I just introduced right now is the setting of learning augmented algorithms. But in the next slides, I will present it more formally and talk about what are the challenges and problems that we might encounter. So what is a learning augmented algorithm? If we consider an algorithmic problem of decision making under uncertainty, such problem has some unknown parameters x1 to xk. For example, in the binary search problem, the unknown parameter was the index where our target is. In the rent or buy problem, the unknown parameter was the number of raining days, and we can imagine other problems where we have multiple unknown parameters in general. And now we'll have some machine learning model that delivers some predictions y1 to yk of x1 to xk. And the problem is that we don't really have any guarantees on these predictions y1 to yk. They can be good, but they can be bad, I don't know. And the objective is to design an algorithm that can leverage the predictions if they are good to have an improved performance, and in the same case, and at the same time, stay robust if the predictions are bad. So these are the three guarantees that we need in learning augmented algorithms. The first one is consistency. So if the predictions are accurate, I need a very good performance. The second one is robustness. So if the predictions are arbitrarily bad, I need to have a good enough performance, at least comparable to the worst case without predictions. And also I need to have smoothness. So smoothness is a slow degradation from the consistency to the robustness as the prediction error grows. And now an important question is, when can we say that a learning augmented algorithm is good? So for example, for sorting algorithms, we had this complexity of n log n. And as I said, there is an algorithm telling us that no algorithm can do sorting in better than n log n in the worst case. Also for rent or buy problem, without predictions, we had this approximation constant of 2, and we had also a theorem that's telling us that no algorithm can do an approximation constant better than 2. So now in the learning augmented algorithm, we have these 3 quantities, and what is concretely an optimal algorithm? So yes, for example, we have these constants. Is it possible to have an algorithm with better constants? Let's say robustness 1 plus 1 over lambda, and the consistency 1 plus lambda over 2 instead of 1 plus lambda. Can we find something like this? Well, the answer is no. It has been proved that these levels of robustness and consistency are Pareto optimal. So when we say Pareto optimal, it just means that they are optimal in the sense that improve one, we cannot improve both in the same time. So there is no algorithm that has simultaneously a better robustness and better consistency. If we want a better robustness than this, then we need to have a worse consistency than this one. But this leaves the smoothness out of the picture, and a lot of papers have looked at Pareto optimal bounds between robustness and consistency, but didn't really look at smoothness. So among other researchers, I looked at the question of smoothness, and with my supervisor Ziyad, we had a paper in AI Stats this year, where we proved that for the rinse and buy problem, there are multiple algorithms with the same consistency and robustness levels. So the ones I presented earlier, 1 plus lambda and 1 plus 1 over lambda. But these algorithms have different levels of smoothness. And so, of course, we need to choose the one that better suits our use case. For example, here we have, so these algorithms that we had are parameterized with a parameter row. And as you see, when the prediction is perfect. So here, sigma characterizes the prediction error, and here we have the performance of the algorithm. So when the prediction is perfect, so the error is equal to 0, the three algorithms have exactly the same consistency. And also when the prediction is arbitrarily bad in the limits when sigma goes to infinity, we'll observe that also these curves will converge to the same constant again. So they have the same consistency, the same robustness, but the way they depend on the error is very different. For example, if I know that my error is at most 10, so the prediction we had earlier was 70 rainy days, and if I trust that my prediction would not have an error more than 10 days, then it is better to use the algorithm with rho equal 1, as it gives the slowest degradation of the performance as a function of the error. And of course, if I choose the algorithm with rho equals 0, then this algorithm is not very efficient here, because for a perfect prediction, we have this performance, 1.5. But then when the prediction error is arbitrarily is positive, but a little is arbitrarily small, sorry, but positive. So a slightly imperfect prediction, the performance abruptly moves from the consistency bound to a much bigger bound, which is not a good behavior. So here, for example, the green curve is much better than the blue one, at least for small prediction errors. So we observe the same thing for another problem that is called one-max search. So again, the problem of one-max search is a little bit the problem I presented in the beginning of deciding when to buy or when to sell your Bitcoin or gold, for example. And so there are algorithms that have the same levels of robustness. So here robustness is R, and the consistency is 1 over R theta. So R and theta are parameters of the algorithms. But then, so we have two algorithms that have the same levels of consistency and robustness, but how the performance depends on the error. We have an algorithm that is much better than the other. So this tells us that looking only at the consistency and robustness for characterizing how good is an algorithm is not enough. And we really need to look at smoothness also, because it makes a lot of difference in practice. So to recap on this section, uh, so again, in learning augmented algorithms, so this is the session I talked about. Now the objective is to find algorithms with the best possible trade-offs between these three quantities, so between consistency, robustness, and smoothness. And what you observe in a lot of problems is that we have trade-offs. So as written here, we have trade-offs between these different constants. So if we improve consistency, the robustness becomes worse. If we improve robustness, the consistency becomes worse, and we need to tune our algorithm to have the best trade-off that is useful in our use case. So now I'm going to talk about some applications that I worked on of learning augmented algorithms. So the first one is the scheduling problem. So a scheduling problem is a typical problem where we have multiple unknown variables, x1 to xn. So more concretely, and in this problem, we'll have, of course, multiple predictions. So more concretely, in the problem of scheduling, we need to schedule n tasks on a machine. So imagine you have a computer and you have n tasks that you need to process on the computer, so that you need to run, and the objective is to minimize the sum of their completion times. So intuitively, it means that we want to finish as many tasks as possible very quickly. The problem is that the time of execution of these tasks is unknown. And if we denote them by xi, so xi is the execution time of task xi, which is unknown, the question is how to schedule these tasks. So just to explain a little bit the problem, imagine we have two tasks with lengths with execution times x1 equal 1 and x2 equal 5. If we run x1 first, then x2, then x1 will finish at time t1 equal 1, and x2 will finish at time t2 equal 5. Yes, so sorry, here x2 is equal to 4 and not 5. X2 will finish at time 5, which will give the sum of completion times equal to t1 plus t2, which is 6. If I execute them in the inverse order, then x2 will finish at time 5, and t2 and x2, sorry, yes, so sorry, x1, this one will finish at time 5, while x2 will finish at time 4, and so the sum is 9. And we can also execute them in parallel. Let's say we process them in parallel with the processing power 1/2 each. Then x1 will finish at time 2, and x2 will finish at time 5, which will give a sum of completion times equal to 7. So this is just to say that even although x1 and x2 are fixed, depending on how we schedule them, the sum of the completion times is different. And the objective is to minimize this quantity. And here, for example, we see that it is minimized for the order of executing x1, then x2. And in general, we can prove that the optimal thing when we have n tasks is to schedule them from the shortest to the longest. But the problem again is that these job sizes are not known. Now, there is a paper that studies this problem in the learning augmented setting. So they imagine that we have predictions y1 to yn of x1 to xn. But in general, in more practical scenarios, there is no reason to have predictions of all the variables. It is also possible to only have predictions of a few variables. And this is what we looked at again with my supervisor. And we had a paper in last year's ICML on this topic. So in the first figure, so the figures to the left, we just show the consistency and robustness trade-off that we talked about earlier. So you don't need to worry about all these descriptions here. I will explain the figure. So the oblivious algorithm that does not use the predictions, its performance is characterized by this dotted curve, blue dotted curve. So its performance is somewhere near 1.8 for any prediction error. And we can have different algorithms that have different levels of consistency and robustness. So for example, the green curve corresponds to an algorithm that fully trusts the prediction. So if the algorithm fully trusts the prediction, if the prediction is perfect, so the error prediction is equal to 0, the performance is significantly improved compared to the blue curve. But as the prediction error grows, the performance also arbitrarily degrades. Now we can have an intermediate behavior. So these orange and brown curves, where we have a performance, so a consistency that is 1.6, a little bit, somewhere in between 1.8 and 1.4. But the advantage is that if the prediction error grows, my performance is never much worse than 1.8. So I have an improved consistency, a degraded consistency compared to the green curve, but my robustness is improved. So this is just the impacts of choosing different levels of consistency and robustness, but there is also the impacts of the number of predictions that we have. So here we assume that we have b predictions out of n, and if b is equal to 0, this just means that we don't have any prediction. And so we just have, again, the constant 1.8, same as here. Now, if as b increases, and if we fully trust the prediction, then the consistency improves. So again, if we have, obviously, if we have zero prediction, uh, and if the predictions are accurate, this is worse than having, let's say, 10 predictions. And if I have 20 predictions again, it's better. So the more knowledge I have, the better consistency I have. This is true. So this is what you observe here. Larger values of B give better and better consistency. So in the case where B equal 50, which is exactly n, we have a consistency of exactly 1. So this is a perfect approximation constant. But the problem is that, again, the better consistency we have, the worse robustness we have when the prediction error is arbitrarily bad. So this is, again, just to stress the trade-off that we have between consistency and robustness. So we also, I also had another paper with Christian Koister, who is in Oxford, and it was published in last year's NeurIPS. So in this paper, we try to design learning augmented priority queues. So priority queues are data structure that needs to perform these operations. So insertion, extracting the minimum, finding the minimum, and decreasing the priority of an element inside the priority queue. So when I say data structure, it's similar to, let's say, examples of data structures include lists, for example, or dictionaries or hash maps. So dictionaries in Python or hash maps in C or Java. And priority queues are, of course, a fundamental thing in computer science that are also used in implementing machine learning algorithms and lots of things. So it's very, very interesting to look at data structures and in particular priority queues, since they have many applications, such as in sorting or implementing shortest path algorithms, minimum spanning trees, scheduling, load balancing problems, network problems, also in ML algorithms such as hierarchical clustering and many others. So what we do in this paper is that we imagine that when an element is to be inserted in a priority queue, we have somehow a prediction of where it should be inserted or the order in which it should be inserted. I don't want to go a lot into the technical details because I don't think they're very interesting for this talk, but I will talk about the results we obtain. So this number of classes divided by n measures somehow the prediction error that we have. So 0 corresponds to a large error. So yeah, so 0 class corresponds, sorry, yes, to a large error, while uh, one class corresponds so sorry, n classes, which is number of classes divided by n, corresponds to a perfect prediction. So here we have our algorithm. So this is for learning augmented priority queue with different types of predictions. And what we see is that when we use predictions, we always have something that is better than standard priority queues. So the brown and pink curve correspond to using binary heaps or Fibonacci heaps, which are possible implementations of priority queues. So with binary heaps and Fibonacci heaps, this is the performance that we obtain, and this is, of course, independent of the prediction. But then we had other algorithms that use the predictions, and when the prediction becomes better, the performance becomes much better than those of binary heaps and Fibonacci heaps, so significantly better than them. And so we test this in different prediction settings, and we always have the same observation. So this is for sorting. And we also implement this for Dijkstra's algorithm. So for Dijkstra's algorithm, again, here we have the performance that we obtain using Fibonacci heap and the performance that we obtain using binary heap in implementing Dijkstra's algorithm. And we can use so the learning augmented priority queue that we designed in our paper with different types of predictions. So the different types of predictions that we use correspond to the blue, orange, and violet curve here. And as you see there again, if the prediction is arbitrarily bad, then they're a little bit worse than Fibonacci and binary heaps. But as the prediction becomes better, they become significantly better than uh, the priority queues that do not use predictions. So this is again just another experimental setting that stresses the same idea. And now finally, I want to talk about some other applications that I find very nice. So these are not applications that I worked on, but that are in other papers. So mainly an application in reinforcement learning. So I don't know how familiar is everyone with reinforcement learning, but I will do a very quick recap of what it is. So in reinforcement learning, we have an agent or an AI, let's say, that interacts with an environment. And so it's a process of sequential decision making, and at each step, the agents must take an action, AT. So this action impacts the environment. The agent receives some reward, RT plus one, and moves to a new state, ST plus one. And so this process repeats again. So here the agent receives this reward, it moves to a new state, and it takes a new action. Again, from this new action, it receives some reward. The reward depends on the action and on the state. And so this process is iterated. And the objective of the agent is to maximize the total reward somehow. So more precisely, is to maximize the regret, but let's say it's to maximize the total reward. So the difficulty in reinforcement for unknown. So in the beginning, I know what actions I can take, but I don't know what reward I will get from a new action. Imagine, for example, you have a baby, a human baby, and so the human baby interacts with the environment, but in the beginning, the baby does not know that if they touch a hot surface, they will get hurt. So in the beginning, someday they touch a hot surface and they receive a reward that is negative, so a penalty, and they learn that they must not touch hot surfaces. So they get this reward and they learn something that in the state of having a hot surface, they must not touch it. And the better action is to avoid this, for example. And with this, we learn a lot of things. So the difficulty is that since we don't know the rewards and the transition models, so the state transition models, there is a trade-off that needs to be done between exploitation and exploration. For example, imagine you are used to eat in some restaurant and there is a new restaurant that is opened. So you can either go to the usual place you go to and you know that they have dishes that you like, or you can take the risk of going to the new restaurant and well, let's say this restaurant has 10 plates. You can go to this restaurant or to this one. If you go to this one, you will test their plates one by one. Uh, but yeah, so you will test, for example, a first plate. The next time you want to go to a restaurant, you must again make this decision. And this decision, so there is this trade-off between exploiting the knowledge that you already have. So you know that you like the dishes here, and the one dish that you took here was okay, but not very good. So you can either go to the usual place or you can go to this new place and explore a new dish again. So there is always this trade-off between exploitation and exploration. This is the whole difficulty in reinforcement learning. And so just a particular case of reinforcement learning is the tabular case when the number of states and the number of actions is finite. And in this case, the objective is to learn the Q table Q of SA for each state S and action A. So this value Q tells me that if I am at state S and I take action A, the reward I will receive is Q star of SA. Okay, and this reward I don't know it in the beginning, and I need to so explore sufficient time to learn the true value of this reward. So an application of reinforcement learning, for example, in advertisements, in recommendation systems in general. So imagine that you have a user who visits a website W, and the website W displays an advertisement of a company C. So the website is paid by multiple companies to display their ads. But then when a particular user visits the website only displays one advertisement from one company. And let's say that the website W gets paid by the company C if the user clicks on the ad. Okay, so this is a model that was used for a long time in recommendation systems for advertisement. And so the difficulty here is that if I am the website, so if I am the website from the point of view of the website, when a new user arrives, I observe multiple informations on the user, which are its location, its age, for example, or interests. If you imagine that the website is Facebook, for example, so the website has tracked the history of the user, their interactions, their posts. So they have some information of the user. So this is the state that we are at. And the action to make by the website is to decide which action, advertisement, sorry, to show to the user. So this choice will depend on the state, on all this information that we have on the user, and the reward is how much the company C will pay W, so me, after displaying the ad. And this, of course, depends on the user action, if the user clicks on the ad or not. So now, after many interactions with users, with companies, the website W, for when a user comes to the website is able to say, okay, this type of users, here are the ads that they might be interested in. They show them one of them, and the user will click on the ad or not with some probability. And depending on this, the website gets some reward. Okay, so after a few years, we have this table Q star that is learned in a very well manner. But now the companies decide to change their contracts with the website W. So in the old model, the website W is getting paid by the company C if the user clicks on the ad of the company C. But in the new model, W will get paid by C only if the user not only clicks on the ad, but clicks on the ad and purchases the products. And this is a true transition that's happened in advertising. It is not a hypothetical scenario, it is really something true that's happened. So now, once we are in this situation, what should we do? So the website normally needs to learn a new table, let's call it Q star new, for the new model, because the reward is not the same. So the states are always the same. The states are always the attributes of the user that we observe, that the website observes. The actions are still the same. So the website needs to decide which action to show to the user, but the reward is not the same. It's again how much C pays W after displaying the ad, but the rules of the reward are not the same. They changed. So the table Q star that we learned is not true anymore, and we need to learn a new table. Now the problem is that we don't want to learn from scratch again, and we want somehow to use this old table Q star that we already learned to accelerate the learning of the new table Q star new. Okay, so yeah, this is the idea. So to use the table Q star somehow as a prediction of the new table Q star new, and for this we can use learning augmented algorithms again. So this table Q star new of SA is a matrix of a lot of unknown rewards that we need to learn. Okay, so these are, let's say, I don't know, n by m parameters, and these Q star that we already learned in the past will serve as predictions of all these parameters. So for each SA, Q star of SA is a prediction of Q star new of SA, and we can study this in a learning augmented setting. So this was done in two papers. So the first one, Can Q-learning be improved with advice? That was published in CODE 2022. So CODE is a very prestigious conference on theoretical machine learning. And another paper, Beyond Black Box Advice, Learning Augmented Algorithms for NDPs with Q-value predictions, that studies a similar problem, and it was published in RIPS 2023. Yes. So yes, this is just to say that there are really a lots of possible applications, even applications of in machine learning of learning augmented algorithms. So I will end my talk here. I will just state some final remarks. So the first one is that the system of learning augmented algorithms is very generic and can be applied to multiple problems. So as we saw, it can be applied to the design of data structures. It can be applied in online algorithms, so to find the best approximation constants. It can be also applied in accelerating machine learning algorithms. So I gave an example with reinforcement learning, but it's also had applications in classification problems, in online regression, and in strategic learning. So there are many papers on this. And the good thing in this field of learning augmented algorithms is that it brings together researchers that work on machine learning and also on theoretical computer science. It is really a field in the intersection between these two major fields, and so there are lots of new ideas. People are working on lots of different topics, and it's very interesting. And for people who might be interested in reading a little bit more about this, there is a list of papers that is concatenated in this website. So algorithms with predictions. You can find a list of more than 200 or 250 papers there, uh, and they are sorted by topic and by which techniques they use, and they can be very interesting. So thank you very much for your attention. I will stop my talk here, and I'm open to having questions or discussion.
بغيتي نقول شكرا للسي زياد حيت لبى الدعوه
شكرا بزاف، شكرا بزاف السي
ميرسي
بهاء، الله
زياد.
يحفظك. شكرا.
الله يحفظك.
شكرا بزاف على الانفيتاسيون، راه زعما الفرح نجي ندير تورك عند ام دي اس.
كوثر بغيت عافاك كنسولك واش تيقدروا يصيفطوا دي كومونتير الدراري اللي في مود سبيكتاتور. داكور فوالا سا مارش. يعني اللي بغى يسول شي كيسيون يسول ولا من مور لو جو داكور. La seule question اللي كلشي جاب صحيح. By the way كان الصوت ما تنسمعوش. Music زعما. الوغ باقي معنا زياد اللي عنده شي سؤال يسول ولا يهز يديه ولا انا نطلعوا كلشي كونتريبيوتور انا كلشي صيفط له لانفيتاسيون. وي الوغ يس هذا انا تولك رقم شحال؟ دونك تولك رقم 7 غادي يكون غدا اون كولابوراسيون افيك واحد الكلوب ديال اي ديال واحد ليكول كاينه في كازا سميتها S2-Ep6 اللي هما اون باراليل دايرين واحد الهاكاطون انترن مع بعضياتهم بات مع السبعه واقيلا غادي يكون عندهم محسن الخديسي وانا غادي نكون مع الثمانيه. دونك غادي نهضر على from idea to AI how to build chatbots and AI applications ولا كيفاش يكون عندنا features ديال AI في some apps ديالنا avec les deux méthodes بالكود وبنو كود. ça veut dire غادي يكون like a workshop وغادي يكون معنا ليكيب ديالهم ديال داك الكلوب وغادي يكون اوسي واحد الصديق ديالنا اللي هو سي ان بروف تيقرا تماك سميتو محمد الطلحاوي. دونك البوست غتلاح اليوم و اسيي دو مرحبا بكم الا بغيتو تحضروا. دونك لاسيس وخلاص كوثر راح تكون فورمولير ديال pour avoir la certification ديال السيرتيفيكا ديال هاد السيشن وما تبارطاجيوش مع اصحابكم جات الناس اللي بقاو حتى الاخر. ثانك يو.
شكرا على لا كيسيون. reinforcement learning utilisant machine de Turing هو نورمالمون اللي كاين ان لي ماشين دو تورين شنو هما لي ماشين دو تورين بحال هما واحد الموديل سامبليفي ديال لونغاج بروغراماسيون وكاين شي حاجات اللي كيقولوا ان اي حاجه تقدر ديرها بان لونغاج بروغراماسيون بحال بيتون يمكن لك تكتبها بان ماشين دو تورين على باز. دونك يمكن لينا نقولوا ان مثلا رينفورسمنت ليرنين يقدر يتكودا بماشين دو تورين ولكن ماشي متاكد واش هذا هو زعما واش هادشي اللي عليه لا كيسيون. زعما لا كيسيون واش نقدروا نكوديو لي زالغوريثم ديال الماشين ليرنين باستعمال لي ماشين دو تورين. نورمالمون ممكن ولكن زعما يكونوا صعابين بزاف حيت بحال دابا الناس كيخدموا على لي ماشين دو تورين راه غتشوفوا مثلا ان غير باش تكتب اون بوكل فور تمشي تحسب اون سوم 1 زائد 2 حتى زائد 100 دير هذه بون ماشين دو تورين فيها بزاف ديال لي زوبيراسيون صعيبه. يعني باش تكودي دي زالغوريثم بحال ديال رينفورسمنت ليرنين نورمالمون راه ممكن ولكن فهمتي صعيبه بزاف زعما. صافي هي السؤال داكور. والله شكرا بزاف عاوتاني. السلام عليكم.
وي شكرا خاي زياد.
مرحبا شكرا.
نشوفوك لو بليتو بوسيبل ان شاء الله.
ان شاء الله شكرا. سلام.
باي باي. يوتيوب حبس. اوكي.